CRYSTAL-AMAZE application demonstration. HyPR-Sim is an application consisting of several simulators. Among the simulators, I will demonstrate the CRYSTAL-AMAZE specifically designed to assist in mixing monovalent and divalent brines at the desired TCT and density. Additionally, the mixed brine can be processed through the PVT simulator to compute its density at the bottom of the hole. Let's begin with the Divalent Brine mixing. As shown in the drop-down menu, 4 options are available to be selected as brine type. 1. Calcium chloride, calcium bromide. 2. Calcium chloride, zinc bromide. 3. Calcium bromide, zinc bromide. 4. Calcium chloride, calcium bromide, and zinc bromide. Currently, the default density values for calcium bromide and zinc bromide are set at 1.65 Sg and 2.25 Sg, respectively. However, users can adjust these densities as needed. Let's click the Settings button and update the densities to 1.7 Sg for calcium bromide and 2.28 Sg for zinc bromide. For this demonstration, let's select the first option, calcium chloride, calcium bromide, 1.7 Sg. Next, it needs to input the required brine density and TCT. The units for these inputs can be customized in the Unit Selection section. Let's click on Settings to explore the options. Density units. The drop-down menu offers 9 unit options such as Sg, ppg, pcf, kg per liter, kg per cubic meter, psi per foot, psi per 1,000 feet, and some more. Temperature units. Users can choose between degrees Celsius and degrees Fahrenheit. For this demonstration, let's keep the density unit as ppg and the temperature unit as degrees Fahrenheit. Assume we need brine with a density of 11 ppg, which is approximately 1.32 Sg, and a TCT of 10 degrees Fahrenheit. Let's verify salt feasibility before running the simulation. Let's check if calcium chloride alone can deliver the desired brine density and TCT. Navigate to the salt rock section and examine the calcium chloride salt table. Highlighting the 32 and 33% by weight calcium chloride row and the corresponding TCT column, we can see that calcium chloride at 32 to 33% by weight is capable of delivering a brine density of 11 ppg with a TCT ranging from negative 19.5 degrees Fahrenheit to negative 6.9 degrees Fahrenheit, which is lower than our desired TCT at 10 degrees Fahrenheit. Thus, it can be concluded that calcium chloride alone is sufficient to meet the required brine density and TCT. Now, let's return to the Divalent Brine mixing section and run the simulation. The results confirm that calcium chloride as a single salt can deliver the required brine density and TCT by blending the following components. Water, 87.47% by volume, which is equivalent to 306.597 pounds per barrel. Calcium chloride, 94 to 97% purity. 12.53% by volume, which is equivalent to 156.04 pounds per barrel. The resulting mixed brine has the following properties. Calcium chloride brine at 32.173% by weight, density at 1.32 Sg or 11 ppg. TCT, negative 10.5 degrees Fahrenheit, which is equivalent to negative 23.6 degrees Celsius. Now, let's maintain the same brine type and adjust the density to 14 ppg, which is equivalent to 1.678 Sg with a TCT of 10 degrees Fahrenheit. Then run the simulation. As shown, a blend of calcium chloride and calcium bromide brine delivers the desired density and TCT as follows. Calcium chloride brine at 34.564% by weight, it has a density of 1.342 Sg and a TCT of 10 degrees Fahrenheit, comprising 6.58% by volume of the final brine. Calcium bromide brine at 1.7 Sg comprises the remaining 93.42% of the final brine volume. To achieve this, the calcium bromide brine must be spiked with dried calcium chloride flakes to increase its density from 1.7 Sg to 1.704 Sg while maintaining a TCT of 10 degrees Fahrenheit. Finally, blending 93.42% by volume of the spiked calcium bromide brine, 1.704 Sg, with 6.58% by volume of the calcium chloride brine, 1.342 Sg, results in a final brine density of 14 ppg with a TCT of 10 degrees Fahrenheit. Now, let's keep the same input data but adjust the brine density to 14.5 ppg and run the simulation. As shown, the blend of calcium chloride and calcium bromide brines fails to deliver the desired density of 14.5 ppg while maintaining a TCT at 10 degrees Fahrenheit. The maximum density achievable under these conditions is 14.198 ppg with the following composition: 99.5% by volume calcium bromide brine at 1.7 Sg, 4.277 pounds per barrel of calcium chloride, 94 to 97% purity, added as dry flakes. Okay, to meet the requirement, let's select the combination of calcium chloride, calcium bromide, and zinc bromide and run the simulation. As per the results, the first step is to spike the calcium bromide brine by adding calcium chloride, 94 to 97% purity, in the form of dry flakes to achieve a density of 1.703 Sg, as follows: 93.233% calcium bromide brine at 1.7 Sg, 3.358 pounds per barrel of calcium chloride, 94 to 97% purity, added as dry flakes. The spiked brine makes up 93.63% by volume of the final brine, which has a density of 1.703 and a TCT of 9 degrees Fahrenheit. The remaining 6.37% by volume of the final brine comes from zinc bromide brine, 2.28 Sg, which has a TCT of 15 degrees Fahrenheit. The blend of spiked calcium bromide, 1.703 Sg, with zinc bromide, 2.28 Sg, delivers a brine at 14.5 ppg with a TCT of negative 12.5 degrees Fahrenheit. If the calcium bromide brine, 1.7 Sg, needs to be prepared using dry powder, click the info button here to get the required amounts of water and dry calcium bromide for mixing. Next, change the brine density to 16 ppg, set the TCT to 20 degrees Fahrenheit and run the simulation. If calcium chloride dry flakes are unavailable, the salt selection can be changed to the calcium bromide, zinc bromide brine. Click the Run button to simulate the brine composition while removing 11.003 pounds per barrel of calcium chloride from the recipe. I hope the above has given a proper demonstration of divalent brine mixing. Okay, now let's go to monovalent brine mixing. Here, two salts from the drop-down list box can be selected to get the desired brine density and TCT. So, let's assume a blend of sodium chloride and sodium bromide is required. As brine is selected from the drop-down list, the max brine density of the selected brine from the salt table will be shown here. If there is available or prepared brine with a density lower than shown in the text box, then the user can change it to the density of the available brine. Here, let's assume that available sodium bromide brine is 12.3 ppg. Okay, let's consider that brine at 11 ppg with a TCT at 11 degrees Fahrenheit is required. Let's click on the Run button to compute the brine mixing recipe. As the result is shown, the simulator is purposed to mix NaCl brine at 25% by weight, which has a density of 1.193 Sg, equivalent to 9.946 ppg with a TCT at 18 degrees Fahrenheit, and prepare a sodium bromide brine at 39% by weight, which has a density at 1.414 Sg, equivalent to 11.781 ppg. Finally, blend them in a ratio of 42.56% to 57.44% NaCl to sodium bromide respectively to achieve a brine density at 11 ppg, where it has a TCT at 9.7 degrees Fahrenheit. Once the desired brine, either divalent or monovalent, is prepared, it needs to carry the mixed brine into the PVT section to simulate what would be the equivalent brine density at the bottom of the hole. As clear, the brine in the hole would be under compaction, due to over-hydrostatic pressure, which leads to increased brine density, as well as it would be under expansion as temperature increases due to the influence of the local geothermal gradient. In the PVT section, a series of TVD and temperature values have already been entered, with the surface temperature at 88 degrees Fahrenheit and the temperature at a well TVD of 11,400 feet at 342 degrees Fahrenheit. Users can change them to the desired TVD and temperature. Okay, let's refer back to salt mixing and transfer brine composition, which contains water, NaCl, and sodium bromide into the PVT section. By clicking on this button, the brine compositions will be moved to the PVT section. Meanwhile, the same transfer button is available in Divalent Brine too. As you can see, the salt composition has been transferred to the PVT section. Let's click the Run button. As shown here, 3 graphs are plotted as per the following. 1. Temperature versus depth. 2. Density versus depth. 3. Pressure versus depth. Let's move the mouse over the graph located in the middle, where the x-axis represents the brine density and the y-axis displays the TVD values. As the mouse moves across the density figure, the corresponding x and y values are displayed at the top of the graph. Navigate to the well's TD at 11,400 feet to find the equivalent brine density at this depth. As shown, the x value is 10.6 ppg. Additionally, by referring to the computed data in the table, which records true vertical depth, TVD, and temperature, the effects of compaction and expansion are determined. Additionally, the table displays brine density at each depth, the overall brine density applied at each depth, and the equivalent brine density at the bottom of the hole, considering compaction and expansion. In the final row of the table, the overall brine density at the bottom of the hole after compaction and expansion is calculated at 10.6 ppg. To achieve the correct brine density of 11 ppg at the bottom of the hole, the initial brine must be mixed at a density of 11 divided by 10.6 times 11, which is equivalent to 11.415 ppg. Okay, let's return to the brine mixing module, set the desired brine density to 11.415 ppg, and click the Run button. Next, transfer the brine composition for 11.415 ppg to the PVT simulator. Run the PVT simulation, scroll down to the results table, and check the brine density at the bottom of the hole. To print the brine mixing report, click on the Report viewer. Next, select the desired report format, Word, PDF, or Excel, and export the report. Repeat the same process for the PVT report. Thank you for your time and attention during this demonstration. I hope the CRYSTAL-AMAZE simulator has provided valuable insights into the brine mixing process and PVT simulations.